Hello everyone and welcome to the course. In this particular lecture we will be discussing image histograms and statistics. This understanding of histogram of the image and its associated statistics is very important when we go for image enhancement techniques, which are many, which we will be discussing in later lectures. So first, basically what is a histogram? Histogram is a graphical representation of statistics and which give you a visual impression of the distribution of the data, how data is distributed of your image is distributed in a graphical form. So you are having bars, and on one axis you are having frequency, and on the x-axis you are having the values, which are groups, and therefore you see the bars. Very soon I am going to show some examples of histograms and associated images. So histogram provides a basically univariate one variable description of data. Generally when we want to understand the statistics of an image, then individual bands histogram is important to understand the variations which are present in the data, or variations of the pixel values which are present in the data. So image histogram is a type of histogram that acts as a graphical representation of the lightness or color distribution. A color, in case if we are using a colored image, then 3 bands histograms would be there. We can also see the individual histograms or different bands or combined one as well. And the color distribution in a digital image, and it plots the number of pixels against each value, each pixel value. And the histogram are the basis of various spatial domain processing techniques, which are image enhancement techniques, which we will see little later. So histogram manipulation can be used effectively for image enhancement, and histogram can be used to provide useful image statistics as well. And this information derived from histogram are quite useful in other image processing applications, for example in image compression and segmentation, because image compression is also part of digital image processing, which we will be discussing in some later lectures, because of large data sets which is handled in remote sensing and digital image processing, and therefore image compression techniques are also employed to reduce the data or segment the data. So the Y histogram basically is mentioned that this is the frequency distribution in a bar graph, and this is the bar graph which I was mentioning, that here you are having the data or the pixel values. On the y-axis you are basically having the frequency, and this is a distribution of pixels against the frequency. So how many times a range of pixel values, range y range, because for each pixel value we do not have a line, but if for group of pixel values a bar is here or a building is here. So for a group of pixel values, what is the repeativity of these pixels values within that image or within that band. So this is how it is distributed. So it's a frequency distribution is a var that displays how often observed values fall within certain interval or classes, and one can specify the number of classes. That means how many bars you want to have, how many groups you want to have, what should be the width of these groups. So that can also be decided, and relative proportion of data that falls in each class is represented by the height, and that is the frequency. So this gives us the some information in a graphical form which is easy to understand. So it brings basically histogram about how the pixel values are spread or present within an image or a band. The spread of points or pixels around the mean value is another characteristics of a displayed histogram frequency distribution. Like here it's a normal distribution, when sometime you may be having not very high pixel values within an image, so you may get a distribution something like this, or you may be having very high pixel values within the same image, then you may be having a distribution. But this is a very normal kind of distribution. Gaussian distribution is there, but generally in images you may not get this kind of distribution. So the variance and standard deviation for the black frequency distribution as shown here are greater than those of or the red frequency distribution. So just looking at histogram, lot of statistics can be assessed about the image, and what image processing or enhancement technique has to be employed will be based on that decision, is going to be based on the how the histogram looks for an image. So like in this one, I am having one example here that this is positively skewed distribution. So that means the lower values are having very high frequency, and this is not a normal distribution but a positively skewed distribution which we are seeing, and these mean values and median values are very close by. So the histogram or the frequency distribution is also characterized by its shape. The coefficient of skewness is a measure of the symmetry of the distribution, and for symmetric distributions the coefficient of skewness is 0. So if I say that means that if it's a Gaussian distribution, then the skewness will not be there, and therefore the coefficient of skewness will also be 0. If distribution has a long right tail of large values like in this example, then it is positively skewed, and if it has a long left tail of small values, then it is negatively skewed. So by looking just shape of histogram, lot of information can be derived, and the mean is larger than the median, and like here it is that if this mean is larger than the median for positively skewed distribution, and vice versa for negatively skewed distribution. So right histogram, this one shows a positively skewed distribution which we are seeing here. This is the image is also shown here, and corresponding histogram is shown. So you can see that if there is this lighter shade areas are there, maybe water body with sediments and other things having higher values, and therefore you are seeing one peak which is corresponding to these brighter areas, and then you are having also darker areas, and so darker areas are represented here, and the brighter areas are represented later on here. So there are two major lobes which are present, which are representing the pixel values which are present in the image. So for a very simple interpretation, we can say that there are the areas, a large number of areas which are having darker pixel values which are represented in the first part of the histogram, and then lighter values or lighter pixel values having high pixel values are represented in the second this lobe of the histogram. The histogram of an image represents the relative frequency of occurrence of various gray levels in the image. Gray levels, sometimes we also call them digital number, pixel value, and so on. Gray levels when we are having a single band and presenting as in a gray scale, so we call in gray levels. So an image in a single band of digital remote sensing data is a representation of how the radiant energy reflected or emitted by the surface is distributed in two spatial dimensions, and the energy is expressed as dn or digital number pixel values, and which is a display are represented by variations in the brightness showing as different gray levels. And since the eye is capable of distinguishing only about 30 gray levels in black and white, this is human eye is not that sensitive that we can distinguish more than 30 gray levels, whereas in colors we might be having more capability. But when we are having a single band image, though in a standard image processing techniques we normally go for 8-bit image, that means a total 256 variations we can have in an image. So an image can be expressed also statistically as probability of finding digital number of a given value within it, and this measure is properly termed the probability distribution function, or in short we call the PDF. So PDF is represented most conveniently by a histogram of number of pixels which are present, which regardless of spatial position within an image and have a particular DN. So whatever the distribution, wherever they are located, in histogram it becomes immaterial, only their pixel values and the number of times the same pixel values have appeared, that will go as a frequency. So this probability distribution function, which you can see here, that this is the histogram and a cumulative frequency on the y-axis and digital numbers as in simple as in histogram. So here are plotted, and these curves will bring you the PDF. So number or frequency of pixels assigned to each digital number DN are plotted as bars against DN in case of histogram. Each division on DN axis is termed as a bin, and is the width is the 1 bar. And in vertical axis of cumulative frequency, here the y-axis of pixels having DN less than a particular value. For example, the cumulative frequency of DN equal to 50, that is F50 plus F49, 48, so on till 0, F0, so that the cumulative frequency of maximum DN is 100%, and the same distribution of DN appears as peaks and sometimes troughs in A, and as in case of histogram, and then the gradient in the roughly S-shaped curves here, what we are seeing here. So histogram of DN frequency is probably the most useful measure in digital image processing, and its shape indicates the contrast and homogeneity of the scene. So for instance, a scene of homogeneous surface with a low contrast will produce a histogram with a single or sharp peak. So if an image, generally when images are acquired by satellite sensors, they do not have much contrast, and so if you look the histogram of a raw image, you may not find a very good quality of image for interpretation. And because if you see the histogram will be the values or these bars of histogram would be on the lower side, and the values might be having very low value. And if the image belongs to like a dense forest area, almost all areas within that image are forests, then all will produce a large single peak, or maybe a large water body is present, then you will have a very sharp single peak within the histogram of that particular image. So basically histogram is a statistical representation of pixel values of an image. So accordingly, whatever the features which are present, they will be reflected in the histogram. But in generally raw image will have histograms in the if you think in terms of x-axis, then in the initial values, there the histogram will be located. So broad single peak, if you are having a single sharp peak, then you are having homogeneous surface with low contrast scenario, and when you are having a broad single peak, which is suggest again homogeneity but a wide range of contrast. So interpreting histogram will let you know, will allow you to understand that which enhancement like a linear contrast or non-linear contrast or histogram equalization, which enhancement technique one has to employ to improve the quality of image for image interpretation. So images that contain several distinct types of surface cover may show multiple peaks. So if you are having an image which is having large water bodies, also having snow areas, maybe sand bodies, maybe forest, maybe agricultural land, maybe built up land within one image, it is possible. Then you will have multiple peaks within the histogram of that image, and each of these peaks will have a significance with different average brightness and will clear separation between these peaks. So that means if the pixel values are occupying the entire range, that means that they are occupying the entire x-axis, that means there is a good features are there and less enhancement may be required. But this is very rare it happens, because generally it has been found that in raw image your bars will be on the initial or lower side of pixel values. As their average brightness becomes more alike, so the peaks will begin to merge. If the features are having same kind of characteristics, means same kind of pixel value, then you don't see these distinct peaks. And other safe attributes of histogram gave a kind of statistical shorthand of an image. The presence of trails and the degree of asymmetry, which we have discussed, of the peak, both indicate important structural features in an image that will be rarely obvious from other pictures itself. So there are two examples. One, this image we have already seen corresponding histogram. Now another image is taken here, and here you have water bodies and some darker rocky areas. Here you don't have water bodies, but some forest and some other light colored rocks are there, light tone rocks are there. So different kinds of terrain sometimes produce contrasting histograms. Here you are having two peaks, here you are having single one sharp peak is here for this image, because you don't have two types of distinct features as seen in first one. And then this image of belongs to Andes mountains has a simple probability density function here, which gives a nearly symmetrical unimodal histogram, even though areas with distinctly different DN values are visible. So a histogram can tell a lot about an image, and also it can indicate that what kind of image processing techniques would be required to be employed in this case. So that is why it is important to understand first before we go for any image enhancement techniques. Now it is not only that you will be handling in digital image processing only one band or single band image. We go for multiple, because now people are not only talking multispectral but hyperspectral remote sensing. So there are hundreds of bands are there. Well, initially from one band, that is a single histogram, if we go for two-dimensional histogram, and then this kind of distribution that will be through a scatter plot is possible. And it says that multispectral data can be expressed in multidirectional histograms, as you can see, or multidimensional histogram, and the simplest of which is the two-dimensional histogram, or also we call as scatter plot. So in a scatter plot, instead of having bars like in a simple histogram for single band, now we will have points for each pixel values, which is corresponding to another band. So suppose here in this case you are having a red band displayed in an x-axis, and a very near infrared band is displayed in the y-axis. So now the values which is having, say, value here which is having a pixel value 100, and in red band having value say 50, it would be plotted somewhere here. So instead of having bars in a scatter plot, you will have a just point which will link to or correspond to the pixel values in both the bands which are present there. But in graphical forms, maybe two-dimensional, maximum three-dimensional, such histograms are possible, but beyond that in graphical forms it is not possible. But from a statistical point of view, it is possible to involve as many as one can think or required to be seen the statistics. So these are simply basically also called as bivariate plots of pixel values for one band against those for another, and they display visually the degree of correlation between the two bands. If you are getting all pixel values are plotted along a line here which is starting roughly from 0, and that means they are having a very high correlation. But if it is just a reverse case that the most of the values are getting plotted something like this, and then you are having a completely different, two different bands, maybe belonging to two different parts of EM spectrum. So one has to see, like when we interpret for single band we interpret the histogram, similarly in case of a bivariate plot or a scatter plot, we have to make interpretation whether how they are correlated or not. And There are some other applications of bivariate plots in maybe in the next lecture, in which we will be discussing how these can be exploited in case of decorrelation stretch, principal component analysis and others. So these are also important to understand that distribution and correlation between different bands which are present in a multispectral image, and also will allow you to choose later on which enhancement technique will be required. So like in this one, the vegetation is getting plotted here, whereas bare rocks and soils are plotted here, and the water which is having high turbidity, this turbid water, is plotting on this lower right side. So this can give us lot of information about the image, and also the biscatter plots also allow us, or they are used while image classification is performed. So they are very important to understand. So the density of plots of individual pixels is a measure where the peaks in the one-dimensional histogram coincides. If you are having density, high density, that means in two bands they are having the almost same pixel value within the scatter plot. Highly correlated data or classes of surface materials that have similar appearances on image of two bands plot near straight lines on the two-dimensional histogram. That means the both bands, the pixel values are highly correlated. And from principal point component analysis, or even in image classification, or even for false color composite generations, then one band can be redundant in that case. So we can drop while making certain. So sometimes when you are having, like in case of Landsat, you are having 6-7 channels present with you. You don't know which 3 channels which you will use to create a color composite. So the best thing first to do such analysis and see that which bands are correlated. So if 2 bands are showing a very high correlation, that means they are having a 45-degree straight line, that means they are highly correlated. So either band can be taken for color composite. Whereas the bands which should be taken which are having very less correlation. Poorly correlated data show shapeless clouds of points, as you have seen in this particular example, that you are having a shapeless clouds of points in which overall poor correlation stems from the scene being a mixture of variable vegetated surface, bare rocks, soils and water. So when all kinds of these such natural features are present within one area, within one image of different bands, then you may get a shapeless a cloud well distributed within this two-dimensional space. So the rock and soil show high correlation, and that occurs throughout the scenes of arid terrain. One other thing which we also use, which is quite close to histogram kind of thing, which we call as lookup table or LUT. So I thought that I can also add this one within this lecture, and LUT allows us to display the values without changing the original value, pixel values of an image. So you are having a sort of a table, and each input pixel will be distributed or will be assigned a new value only for display. So that is called lookup table, as an example is here given, but this instead of 0 to 255, you are having an example of 0 to 2048, and also on the y-axis 0 to 2048 values are there. And if a pixel value is having say 500 or 1000 values, then corresponding the value for display would be somewhere here. So LUT basically allows us to map the input RGB values to output RGB values. It may be LUT, maybe even for single band or maybe color band. So color image using a color transformation function, and these are specified in tabular form using color transformation function, and that function is very simple, that LUT it is through a function x by RGB equal to G x by R and GB. So you can this allows the advantage of LUT, that it allows us do not change the values before display. So this your image is intact, your data will remain always intact. Only for display you will use LUT. So that allows us this kind of flexibility. You can always save LUT instead of creating a new file of your original band, because ultimately what happens, because when you are handling high spatial resolution data, it occupies a lot of space on your hard disk, and nobody would like to have that one. So the best thing is to save the LUT rather than a new enhanced image of that band. So that is why this is LUT is very much required. Now how statistics can be extracted from these univariate descriptive image statistics can be seen or extracted from these. So I will go one by one. First is like mode. So if it is a normal distribution and having a full symmetry, you will have mean, median and mode just one, which is a rare in a natural good images here. So the image which is having high contrast and other things, you may not have this kind of scenario. But anyway, so you are having a normal distribution where mean, median and mode are the same. And if you are having a skewed distribution like in this example, then mean is less, median in between and mode will be having a higher value. So this example of negatively skewed distribution, and the lower one is the positively skewed distribution where mode is having again will have the lower value median and mean is having high value on x-axis. Bimodal, when your image is having two major areas having two distinct variations in the pixel value, then you may have a situation something like bimodal or multimodal distribution, though the mean and median would be in the center, but this bimodal will create a altogether different shape of histogram. And then mean and median are when you are having uniform distribution, that means all pixel values are same, which is not very rare, which is a very rare, except in desert areas you may have kind of images of desert areas, you may have a distribution something like that. So in the last let's look how mode, mean and these are defined. The mode is the value that occurs most frequently in a distribution, and usually the highest point here like on the curve of histogram. It is common, however, to encounter more than one mode in a remote sensing data sets. Like here, we are having two mode. So this is bimodal scenario. So it is not necessary that you will always have one peak, as I have been discussing, depending on the areas which are being represented within one image. So the histogram would be accordingly. Second is the median, is the value midway in the frequency distribution. So this is the, in case of normally distribution, the midway value is the same as mean and mode, but in case of negatively skewed distribution, median would be somewhere here. So the median midway value of the frequency distribution, one half of the area below the distribution curve is to the right of the median and one half is on the left. So if median is plotted, then because it exploiting the distribution or the frequency of your pixel values as well, it incorporates that one. So it is the median of the frequency. So one half is having one number of pixels and another is the same number of pixels. And the mean is simple arithmetic average and is defined the sum of all brightness value observations divided by number of observations, which are displayed here. So basically this brings to the end of this discussion that how a histogram and bivariate plot LUTs can be exploited, can be used before we go for serious image enhancement technique. They will allow us to first to understand how pixel values are distributed of within one image, maybe a single band or multiple band depending on what kind of analysis we are going to perform, and then it will also allow us to understand or to choose that how the enhancement can be performed, so that which image enhancement technique will be adopted. So that is why histogram, bivariate plot and LUTs, these are all important steps before serious image enhancement procedures which go for image enhancement. So thank you very much.